Hello. I'm going to be recording today's worksheet since everyone was a little busy. So we'll just get right into it. The first question is on voltage dividers. And so the main idea with this question is we're trying to distinguish like when and when we can't use voltage dividers, can and cannot. So the first part is just we have these two voltage dividers and we're trying to figure out like some expression for the voltage at this node A and at this node B. So I'm just going to start doing some node voltage analysis. We can label one of the nodes 1 and the other node 2. And we'll just start writing some equations. So we know that U1 minus U0, namely the two nodes across the voltage source, the difference between them is just going to be the voltage that the voltage source is supposed to maintain. That's kind of the job of the voltage source. Then we do it across the resistors, and we know that voltage across resistors is just the current across the resistor times the resistor value. That's by Ohm's law. And so remember, we take the positive one and then subtract out the negative node, since we arbitrarily labeled node 1 to be at a greater voltage than node 2. So there's a couple things I can do here that to kind of simplify this. First, I can notice that U0 is just 0, so I can cross it out. And then I can use the fact that U1 is equal to V. So I'm going to label it using V instead of U1, so that it's clear that I already know this value. Okay, so now I want my current equations, and the only one I have is that I1 is equal to I2. And the reason I can say this is because I look at all the currents entering A, and I see that I1 is entering, and I2 is exiting. And so since I1 is entering, all of it has to go out, so they're equal. Now let's try to use this. Whenever we have these like node equations, we want to convert them to like something in terms of current so that we can plug them into the current equations. So we have I1 is equal to V minus U2, and I'll simply divide both sides by R1. And then for the other one, I get I2 is equal to U2 over R2. And now I'll just plug into the current one. So in the current, I have V minus U2 over R1 is equal to U2 over R2. Okay, now I just have to, let's see what I can do. Okay, I'll move the U2 over R1 to the other side. So I get V over R1 is equal to U2 over R2 plus U2 over R1. And then lastly, I get my answer, which is V is equal to U2. Oh, sorry, I'm looking for U, so let me not do that. Let me actually say my left side is U2 over R1 plus U2 over R2 equals V times R1. V over R1, sorry. Okay, I'll factor out my U2. And in here, I'll just simplify this to R1 R2 plus over R1 plus R2 is equal to V over R1. And then lastly, sorry, this is kind of in the corner here, but you'll get U2 is equal to V times R1 R2 over R1 times R1 plus R2, where I cancel out the R1s. And so as a reminder, what this is saying is that the voltage across this node over here is equal to the proportion that R2 is among the total resistance times the total voltage. So basically, some certain proportion of this voltage is being distributed to this node across this R2. And then the other remaining portion is distributed across R1. And that's why we can say that V times R1 over R1 plus R2 is the other part, is the voltage across R1. So now that we have this, let's kind of just put this in a corner and try to analyze the second part. I think it might be easier to go on a separate page. So I'm just going to try to memorize this circuit and then copy it over R1, R2, R3, R4. Okay. Hello. So this problem, the second part is kind of a mess. I've tried to do this like 2 times already, and it got way too messy. But then I checked the solutions and I realized that it's just a messy answer, so I'm going to kind of restart this. I've already drawn the circuit diagram, so we're going to just kind of go through it. And remember that we're looking for the potential right here at node 2. So let's start writing some equations. So for the nodes, let's look at the first circuit element, which is our voltage source. So across the voltage source, there's above it, there's U1, and below it, there's our ground node. So the first thing that we can conclude is that U1 is equal to the voltage at our ground node, is equal to the voltage at the voltage source. And the way I got that was that U1 minus U0 is equal to V. This is because V maintains this voltage drop. That's kind of the job of voltage source. From here, I'm going to write out equations for across all the other elements, but I'm going to skip a step. Not the first time, but I'll just show you what I'm doing. So I'm going to write U1 minus U2 is equal to the voltage across R1, which is equal to I1 R1. So we know this. This is what we've typically been doing. So all I'm going to do is start writing this R1 below, just to use less space. And then I'm going to do this for all the other ones. So we can say that U2 minus U0 over R2 is equal to I2. U2 minus U3 over R3 is equal to I3. And lastly, U3 over R4 is equal to I4. So those are my nodes. The KCL equations I'm going to write are for node 2 and node 3 because the ground node shouldn't really give us any new information. And at node 1, we kind of have this current through the voltage source, and that's just equal to like I1. So that also I don't think we're going to need. So I'm going to start with these two and then see if we need anything else. So at node 2, I can see that there's one current going in and two currents going out. Namely, I1 is coming in, and it's equal to the sum of the currents going out, which is equal to I2 plus I3. Then at node 3, we have our I3 going in and I4 going out. And this is pretty similar to like the first part, where you just had one current going in and the other one was equivalently going out. So let's try to write in our equations. One more thing I'm going to do is first cross out all these, this U0, and then I'm also going to label this U1 with just the V, because we already know what it is. Okay, so we know that I1 V minus U2 over R1 specifically is equal to U2 over R2 plus I3, which is U2 minus U3 over R3. And our other equation, let's call this equation 1, is a little simpler. It's U2 minus U3 over R3, which is I3, and then that's equal to U3 over R4. Okay, and so the way I'll kind of try to do this is simplify both of these equations until we can solve them. You'll notice that we only really need both of these because we're solving for two unknowns, U2 and U3, and we have two equations, and Gaussian elimination probably drilled in you that if you have two linearly independent equations, you can solve for two variables. Okay, so let me start by simplifying the first one. Okay, and I'm going to start by moving the U2 to the other side. and then try to kind of move all of the, actually, let's try to move all of the u2s to one side, and then maybe factor it out. So what I'll do is say v over r1 plus u3 over r3, which I got from right here, is equal to u2 over r2 plus u2 over r1, which I moved from the other side, plus u2 over r3. And I can erase this and rewrite it as u2 times 1 over r1 plus r2 plus r3. Okay, so we have some sort of an expression in terms of u2 here. So in the second one, let's try to just solve for u2. And so in the second one, we get that u2 over r3 is equal to u3 times 1 over r3 plus r4 and so moving that r3 to the other side, we can just change this and cross that out. Okay, so now that we have this, let's try to plug this in. And so we'll get that v over r1 plus u3 over r3. And now we're going to plug in the value for u2 here is equal to u3 times this huge quantity, r3 over r3 plus r4 times 1 over r1 plus r2 plus r3. Okay, and if that is not intimidating enough, we need to do some more work, because eventually we do want to solve for u2, and we've gotten rid of it. So here's what I'll do. Let's see. Let me try to keep the v over r1 on one side, and then put the u3s together. So v over r1 would equal to u3 times this quantity r3 over r3 plus r4 times 1 over r1 plus r2 plus r3 minus 1 over r3. And this I got by moving the other one, moving the u3 over r3 from the left side. Okay, so now we essentially have an expression for u3. Now all we have to do is kind of just multiply. So we can just say u3 is equal to v over r1 times r3 over r3 plus r4 maybe I'll just multiply out the r1. Yeah, let's do that. R1 and then this giant thing minus r1 over r3. Great. Let me check the answer. I probably messed up somewhere, but hopefully it was minimal. Let's see, they don't have a negative term, but I think other than that, we got it. Let me just go back and see why we are subtracting this 1 over r3. That's weird. I don't know why they didn't make it negative. I will check on Slack. But this should be approximately correct. I know it was a mess, but what we're trying to learn here is that we simply can't treat this as a voltage divider. So the main point is that, like, you might think that, like, you can treat this as a voltage divider and then this separately as a voltage divider, but the reason we can't do that is because the main property that we leveraged in this previous part 1, is that this current through R1 is equal to the current through R2. However, now that we added this extra branch, that's no longer the case because this current's actually going to split up. And so what this is called is loading the circuit. When you have some sort of circuit that works and it produces a certain voltage at A, and then you add another resistor somewhere. And that's like the load resistor. And in this case, it's actually going to mess with like the rest of our circuit, and the voltage at A is no longer going to remain the same. But in the future, we're going to learn about, pretty soon actually, we're going to learn about op amps, which we can use to make sure this like resistor doesn't interfere. So yeah, that's kind of a long and winded first problem. I will see you on the next one. Okay, on to the second problem. So we're gonna do, this one's gonna be related to power, and specifically we're first looking for power dissipated by resistors. So typically, resistors are going to be using power, and voltage sources are going, any kind of sources are going to be generating power. And using power is basically known as like dissipating power. When we use passive sign convention in this V equals IR equation, when you have a positive output, that means you're dissipating or using power. And then if you have a negative one, which is typical for voltage sources, you're generating power. Okay, so now that we have this expression, let's do 1, 2, and 3. So they already kind of gave us the answer to 1. We have this expression that, oh wait, they didn't. Okay, so let's first talk about what power is. And power is given by, in passive sign convention, the current times the voltage. And I think we went over like a derivation of this last time, so I won't do it again, but if you have questions, just email me back. So let's give an expression in terms of VR and IR, and that's the one that we already have, so that's good. The next one, they want it in terms of VR and R. And for this, all we're going to do is rewrite the voltage in terms of the resistance. So we know that VR is equal to IR times R, and so that gives us that P is equal to IR squared times R. Oh, sorry, they wanted VR and R. Okay, I did the next one. Okay, and then they want VR and R, so we're going to get rid of this current. So this current is just going to be, let's do part 2 right here. IR is going to be VR over R, and therefore this power is going to be VR squared over R. So these are kind of our three equations for power. We have IV, V squared over R, and I squared R. And this is obviously only going to work for resistors, because we used resistors in Ohm's law. Yeah, that's the gist of that part. So let's look at this circuit now, and we're gonna kind of analyze it and then look at power. So we basically have this current source, we have 2 resistors in parallel, and then 2 more resistors in parallel. And the way I saw that they were in parallel is because they share the same start and end node. So right here, these two share the same node at the beginning, node 1, and the same node at the end, node 2. And then R3 and R4 similarly share node 2 and our, let's call this our ground node, node 0. Okay, and so that's what question B is asking, which components have the same voltage across them. And that's what really makes them in parallel. So if you'll notice, the voltage across R1 is U1 minus U2. If I label this way. And the same holds for R2, because, again, same nodes. And then R3 and R4 also have the same voltage across them. So this is R1, comma, R2, and R3, comma, R4. Okay. Under what conditions will R1 and R2 dissipate the same amount of power? So we got that power is equal to I of E. But in this case, what's even more useful is to use this expression we have in terms of voltage and resistance. So we got that power is equal to V squared over R. And since the voltage across them is the same, the power across them is going to be dependent on only the resistance. So we want V squared over R1 to equal V squared over R2. And this just means that if R1 and R2 have the same resistance, then they'll dissipate the same amount of power. Okay, that's part B. Let me do part C. Oh, that's part C. Let me do part D. So we're going to calculate the amount of power. This is just going to be some sort of plug and chug. So for R1, we say the power is V squared over R1. Oh, so they gave us the current source value now. So we're going to use that, 1 amp. And so since we have the current and we have the resistances, both of them are 2, we can use the fact that the current is going to split up evenly in parallel. And this is because they have the same resistance. I can prove this maybe later. So we get that I1 is equal to I2 is equal to 1/2, because it's 1 amp divided by 2. And we can use P equals I of E, or I squared R, is equal to 1/4 times R1, or R2, where you get 1/2 ohms of, not ohms, watts of power. Okay. And similarly, this I1 is going to go through here, split up, and then come back together. So the current here is also going to be 1 amp. And so we can use the same property that we just did for R3 and R4. Since they're equal, it's going to split up evenly. So I can say that the power is equal to 1/2 squared times 6 is equal to 3/2 watts. All right, let me just check this once. Okay, it looks correct. Cool. Lastly, we're going to get how much power does the current source consume. And so here they say, hint, consider the conservation of energy. And so what we can notice here is that the current source is the one that's generating the power, and all the other components are using this power. And so what conservation of energy tells us is that no energy is created or lost. So all this energy that's being provided to these resistors is going to be created by this current source. So we can say that the power generated by this current source in magnitude is going to be 3/2 plus 1/2 times 2 for each of the resistors. And so this is going to be 4. And typically we denote this with a negative sign because it's generating power. Oh, and one more thing they did on the answer key is kind of use the property that all the powers must sum to 0. So then you get that these add up to the negative p of is. All right, that's problem 2. I'll go derive the thing I was mentioning earlier, and then we'll do problem 3. Okay, here's the derivation I promised. So basically I have this circuit with a current source and these 2 resistors. And what's happening is I have this current I1 through R1 and this current I2 through R2. So using KCL, I said that the current entering this node 1 is equal to IS, and the current leaving this node 1 is equal to I1 plus I2. So that's how I came up with this first equation. Then I came up with expressions for I1 and I2. Mainly how I did that was I grounded this node right here, and I said U1 minus 0 over R1 is equal to I1. And I did the same thing for I2, except I used R2. So yeah, here we're really taking advantage of the fact that they're in parallel, so they have the same voltage across them. So now we have this second expression, equation 2, and now we're just going to solve for U1. So we get U1, and then we factor out the 1 over R1 plus R2, do some algebra, and get this expression for U1. So lastly, to find the current across either one of them, let's say we want to find the current across R1, we just get I1 is equal to U1 divided by R1 is equal to R2 over R1 plus R2. And so now that we have this, we know that if the resistor values are the same, then this just goes to R over 2R, which is 1/2 times U1. And so that's how we kind of got the thing earlier. Notice that this is kind of the opposite of a voltage divider. So when there's more resistance in a voltage divider, more voltage is provided to it. But here, it's the opposite. When there's more resistance in parallel, less current goes to it. And this is because we're holding the voltage constant. And so the more resistance there is, the less current will want to flow there. So the saying goes that the current takes the path of least resistance. So the lower you make the resistance, more current will flow through there. So yeah, that's the little side note. We'll do problem 3 next. Hello. So this is going to be the Rubik's Cube problem. And I definitely encourage you guys to kind of try and do this on your own, especially since the worksheet kind of tries to walk you through it in like 6 different parts. Yeah, but I'm just going to be going over it. I apologize in advance if the explanations are not as clear. This problem is kind of confusing, but I will try my best. Okay, so we have this Rubik's Cube of a circuit. Kind of try to visualize it in 3 dimensions. This E is like, I'm not going to try to explain it, just try to visualize it. And let's kind of just use the problem parts to break this down. So the first part is basically asking us to group these vertices using the distance of the shortest path from A to a vertex. And so we can see that the path from A to B is one edge, A to D is one edge, and A to E is one edge. And by one edge, that's kind of analogous to just one resistor. And then we have all these other nodes where the path to F is to go through B, and the path to G is to go through D, and the path to C is to go through B or D. And yeah, that's kind of the gist of that part. So let's see what the question is asking. Yeah, so it's just asking us to group them. And so we kind of just did that, where we found some nodes that were distance 1 away and some that were distance 2 away. Note that this node H is distance 3 away, so we'll deal with that later. So first we're going to consider the group of vertices that are 1 unit away from A, and how are they related to each other is what the question is asking. So we have this set of vertices B, D, and E, And essentially how they're related to each other is that the node voltage at B, the node voltage at D, and the node voltage at E is the same. And the reason we can say this is because of the symmetry of the cube and the fact that the resistances from A to B, or from A to D, or from A to E are the same. This means that the potentials at B, D, and E respectively also have to be the same. So what's another way of saying that the potential to the left of a resistor, and the potential to the right of a resistor are the same as that for another resistor? That's right. It means that they're in parallel, or at least they can be treated like they're in parallel. So what we can kind of say is that B, D, and E are three nodes that are in parallel. So mini circuit diagram here, we have node A branching out into B, D, and E. Which are incidentally the same node. Okay? So now we're going to consider all the vertices that are 2 units away. So that's going to be group 2. And that's going to be F, G, and C. And what we want you to notice about this one is that there are 2 distinct ways when you're describing the shortest path from A to these nodes. For example, to get to C, you can go A to B. Let's use a different color. A to B, then B to C. Or you can go A to D, then D to C. Similarly, to get to F, you can go A to B, then B to F, or A to E, and then E to F. And so there's two edges that lead to each of these, 2 edges coming out of the group 1 that lead to each of these nodes in group 2. For example, once more, for C, you can come from B or D, which are both part of group 1. So let's write which ones we have here. So we have C, F, and G. And there are 2 edges each. And since there's 3 nodes, we can do 2 times 3 and get 6 total edges. And so that means that 6 resistors are involved. Okay? And how are group 1 and group 2 related to each other? Well, we have that group 1 is kind of right here, and you can draw an edge from group 1 onto any one of the nodes in group 2. So there are 6 different paths. I use the same kind of inference to conclude that they were in parallel, because we know that B, D, and E are in parallel, and we know that the node voltage at C, G, and F is the same, because using the symmetry of this Rubik's Cube, we said that B, D, and E are at the same node voltage because they're all 1 distance away from A. So we could use the fact that C, G, and F are both 2 distance away, or we can also use the fact that they're 1 distance away from H, which is kind of like the opposite corner of A. And if you just turn this cube around, we'd get kind of the same cube. So these are going to be in parallel. Yes, we can. We just did. And then how far is group H from A? We know that it's 3 edges away. And we're going to try to simplify the path from group 2 to H. So kind of what I mentioned here was that each of these are 1 distance away from H. So drawing the same conclusion, I can draw this backwards this time, where this is node H. And these are my 3 nodes, C, G, and F. Now our middle section is the 6 nodes. My resistors are getting slowly uglier because there are so many. Okay, and then we have the remaining 3. Okay, so now if you'll notice, basically starting from A, we've created a circuit such that if you take 3 steps along kind of any edge, you can get to H. If you take 2 steps, you can get to any of the 6 in the middle, which is basically what we discussed. And if you take 1 step, you can get to our original 1-step distance nodes, which are B, D, and E. Okay, so now we would just want to combine our findings together and find the equivalent resistance. So we're going to use the fact that we know how to combine resistances in parallel. And one trick that I'll show you guys is that if you have the same resistance in parallel, all you need to do is divide by the number of resistors. So you can say that R equivalent 1 is equal to R over 3. This one is equal to R over 6, and this one is equal to R over 3. And you can kind of see that using the parallel equation. Maybe I'll show that separately. But basically we can add these together and get our total equivalent resistance. Now we're using the fact that we can combine them in series by adding them up. So this will be 2R over 3, 4R over 6 plus 1R over 6, which is equal to 5/6R. Cool. Yeah, I might do the parallel thing, but other than that, I will see you in the next problem. Okay, let's do problem 4. This one's going to be superposition, but the first part is just this circuit that we're going to solve. And we're going to do it first normally, and then we'll use superposition in the next part. So there's one more concept in here that we have to talk about first, which is this dependent source. And a dependent source is pretty much just like a regular source, but its value depends on some other value that isn't fixed at first. And so in this case, this is a dependent voltage source represented by this diamond, whose voltage is always going to be 2I2. So this is kind of just like a regular voltage source, where the V is equal to 2 times this current I2, always. And so basically there's no predetermined value. It depends on how you use it. Okay, other than that, we can basically just treat these as normal circuit elements. So yeah, let's get into it. So part A, we're going to do the same kind of nodal analysis. So we're going to have node equations, and then we'll have KCL. So let's first label this. Most of this diagram is already labeled for us, so we're going to take advantage of that. But we just need to label the positives and negatives. So there's a positive here and a negative here because of the current I2. It's going through this way, positive sign convention. Positive here and a negative here because of the current I1. And positive here and negative here because of the current I3. And one more thing, the current here is I1 because of this current source. The current right here in this node has to be I1, and therefore the current through the resistor must also be I1 because there's nowhere else for the current to go. Okay, so let's do some node equations. First, across R1, we can say that Vx minus V1 is equal to I2 times R1. I2 is the current through R1. Then we can say for R2, 0 minus VA is equal to I1 times R2. And the reason we do 0 minus VA is because 0 is our ground node and it's positive, labeled positive. So we subtract the negative from the positive. All right, and across R3, we have VB minus 0 is equal to I3 R3. And there's one more equation we can write, which is for this source right here, which is that the voltage across it, so Vx minus Vb, is going to be 2I2, because that's what we're basically told that this voltage source is going to do. So things to notice here is we know V1, we're looking for Vx, and we have two equations that relate I2. All right. With those in mind, let's do some KCL. So let's write an equation for this node right here. We have I1 entering, and I2 and I3 exiting. So that's what we can write. And for now, let's try to work with this equation and see where we can get. So once again, let's look at what we know. We already know this value I1. So we can even plug it in right now. We know that this is 6. Now we have one less thing to worry about. We can write this in terms of I2 plus I3. So I2, we can choose to write it either way, either using the Vx minus Vb or the other one. Let's say we write it using the first form. Using the first form, we get I2 is equal to Vx minus V1 over R1. Okay, and then for the second one, for I3, we can get I3 is equal to VB over R3. Okay, let's see. Can we write VB? Can we rewrite VB? We should be able to rewrite VB as Vx minus 2I2 using this equation. So this is just Vx minus 2I2. Okay, so now that we have written it this way, let's plug in some more numbers to make it a little less intimidating again, because I don't want it to become like the first problem, because that was super messy. Let's see. So we have Vx, we don't know, but we do have V1 and R1. So V1 is 7 volts, and R1 is 10 ohms, plus Vx minus 2 times I2. So this is minus 2 times the quantity right here. So that's just, again, going to be Vx minus 7 over 10. All divided by R3, which is 2. Okay, and now the only variable we have here is this Vx. So we can do some more algebra and solve. So this is going to be Vx minus, how do I want to do this? Let's say this is minus the quantity 2Vx minus 14 over 5. Oh wait, Vx minus 7 over 5, sorry. Okay, and then at the bottom we have this denominator of 2, and then here we have Vx minus 7 over 10. So maybe we can multiply the whole right term by 5 as well. So we get 5 minus that, and make this 10. So we get our whole common denominator. Okay. Some more algebra, you get 6Vx, 5Vx plus 14, or plus 0 seems. So basically I got this negative 7, and then this negative and this negative got a positive 7. So that should be correct. Over 10 is equal to 6. And lastly, I can do 60 is equal to 5Vx, where Vx is equal to 12. I tried to do this earlier, but only using variables, and it got super bad. So I think when you get something like this, I would urge you to plug in as soon as possible. But yeah, that's just me. All right, I'll come back with the second part. Okay, let's do part B. So basically we're going to do the same thing, but with superposition. So we're going to have to redraw the circuit, and the way we're going to do that is we're going to null out. Oh, let me explain superposition actually. So the main idea behind superposition is that you can null out one of the sources and then find the resulting value of pretty much anything, in this case like Vx, when that source is not present. Then what you do is you add that source back and null out a different source. And then you find the value of Vx with the other arrangement. When you do it by one nulling out all of the sources, in the end, you can add them up and get the value for Vx. That's the basic principle behind superposition. I believe you guys probably did some sort of a proof in class. But for the purposes of problem B, superposition works, so we can use it. One more thing you can't do is use superposition for dependent sources, and so we're not going to do that. So the first thing we can do is just null out this voltage source, and the way we can null out a voltage source is just draw a connection from the node on both sides of the voltage source, and so that would be just like this. And since we connected those nodes, like the voltage source essentially doesn't exist anymore. Okay, I believe I got everything. Let me do some labeling. And we're still looking for this Vx. Cool. So I believe that's it. We're going to use pretty much the same strategy, except node voltage analysis is going to be a lot easier now that we've removed one of the sources. And so here's what we can do. We can write out our node equations. And the first one will just be Vx minus 0 is equal to I2R1. The next one we can do across R2. VA is equal to I1R2. Oh, negative VA, because we had a plus minus over here. The reason I'm doing this a little faster is because we kind of just did a pretty similar circuit last time. So then we say that VB is equal to I3R3. And the last one we had was across this dependent voltage source, and that's just going to be Vx minus VB is equal to 2I2. Okay, so we can actually use the same equation as last time. I1 is equal to I2 plus I3, because that node is still present. And then we can plug in our values. So in this case, we know I1, so that's just 6. And then I2, we can use, let's use, how about Vx over R1, since we don't have that complicated V1 in our expression anymore. And then for I3, we can use VB over R3. But once again, same as last time, VB is equal to Vx minus 2I2 equals Vx minus 2 Vx over R1. So then we just have C6 equals Vx over R1 plus VB, which is Vx minus 2Vx over R1 all over R3. Okay, plugging some values in. R1 is 10, and then R3 is 2. So then we get that, I'm going to do it up here, 6 is equal to Vx over 10 plus, let's multiply the other thing by 5 again, so then we get 5Vx, I guess we'll multiply by 10 this time, or fine, 5 minus Vx over 10. And so as an end result, we get 5Vx equals 60 and Vx is equal to 12. So this is actually the same answer that we got last time, which must imply that when we null out the current source, we're going to get Vx equals 0. Because if you remember, the answer from the last part was just 12 volts. So let's erase this and then do the second part. Alright, so I erased this, and let's basically continue. So now we're going to convert our circuit, and we're going to null out our current source. And so we're going to ask, what does it mean to not have a current source? It means that there's basically no current where the current source is. So the opposite of having this current source is to have an open circuit. So there is a distinction there between, like, earlier when we just kind of drew a wire with a voltage source where we got rid of the change in voltage. Here we're getting rid of the current. So I'm going to try to erase this if possible. Otherwise, okay, I guess I'll just have to redraw part of it. So here's an open circuit. And there's a resistor. And I'm going to have to put back this voltage source. What was it? V1. Okay, so now that I have this open circuit, we're going to do a similar analysis where we still have like our node equations, where we have Vx minus V1 over R1 is equal to I2. And then we can write one for I3, which is VB is equal to, over R3 is equal to I3. So we can no longer write anything for right here, because there's going to be no current that goes here. And the reason why there's no current is because there's an open circuit here. So once the current would reach here, there would be nowhere for it to go. So all the current is actually just going to go through this bottom wire. And so that's why we can basically completely ignore this part and then find Vx. And so here's what we'll do. We'll write the final node voltage equation, which is Vx minus Vb is equal to 2I2. This is again based on our dependent source. And then I believe that's it for those. And then for our KCL, we don't have an I1 anymore, so we just have I2 that's equal to I3. So I3, once again, is VB over R3. And then I2 is Vx minus V1 over R1, which is equal to VB over R3. Now we can actually write this VB again in terms of I2. So let's do that once again. Vx minus 2I2 is equal to VB. And we can say this right here. Vx minus 2 times the quantity I2, which again is Vx minus V1 over R1. And then this is all over R3. Okay, so we don't even need this anymore. Let's do some plugging in of numbers. So we don't know Vx, but we do know V1, which is 7. So V1 is 7 and R1 is 10. is equal to Vx minus 2Vx plus 2V1 over 10 all over R3, which is 2. Okay, we'll do our whole like multiply by 5 thing. So this becomes 5, this becomes, this crosses out, and then this becomes a 10. So then these 10s also cross out, and we get, once again I'm going to move up here. I'll draw a little arrow. Vx minus 7 is equal to 5Vx minus Vx plus V1. And so this will just give us, and oh, what's V1? V1 is 7. So on the right side we can have 14. On the left side we can have, what is this? Vx minus 5Vx, negative 4Vx plus Vx. That's negative 5Vx. I somewhere messed up.
I'm just going to record over this part. Basically where I messed up was instead of saying I2 equals I3, I should have said I2 is equal to negative I3 since they both go outwards. And so as a result, I added 7 and 7 to get 14. Instead, I should have subtracted 7 and 7 to get 0. And so then I would have gotten that Vx is equal to 0 in this case, which would get us our final answer of 12 plus 0. Yeah, sorry about that.